Okay, so good evening, everyone. Am I audible and visible?
Yes, madam.
Okay, thank you. Okay, so welcome to the live session of week 8 of Nonlinear Vibration NOC24 me54. And this course is being taught by Professor S.K. Dwivedi of IIT Guwahati. And I'm Rashi Aditi Ranjan. I am an NPTEL PMRF TA and I'm a PMRF scholar in the Department of Mechanical Engineering, IIT Patna. So I'll be starting with the overview and then I'll be taking on some questions which would help you to solve the assignment problems. So this week's lectures were dedicated to these topics. So initially the discussion was made about limit cycle and what a limit cycle is and how it behaves. So if you people have gone through the lectures, you people know already that a limit cycle is essentially an isolated periodic orbit. Okay, so what is the difference between a periodic orbit and an isolated periodic orbit? So this actually means is that in case of a periodic orbit, like if I take the case of a linear spring mass damper system, or I should not consider the damper for that matter, if I only have a spring and a mass like this. Okay, so what is going to happen? If I give some perturbation, let us say A is the perturbation. So what is going to happen? It is going to oscillate, right? The mass is going to oscillate. Okay, so if it is going to oscillate, then if I try to draw its phase plot, it would be something like this. This is x and this is x dot, right? And this amplitude or whatever the radius of this circle would be, it would depend upon what initial condition I am giving to the system, right? Like for example, this is for let us say A1, then there will be like this another orbit which will be for A2, and there can be another orbit which would be for A3. And how is this going to happen? If I take initial x dot 0 is equals to 0 and my x 0, which means the values of displacement and velocity at time t is equals to 0, it will be some ai. So this is the case when your a1 is less than a2 and greater than a3. Okay, so this is what a periodic orbit is. Okay, so depending upon what initial condition I'm giving to the system, the amplitude is going to change. Okay, but in case of a limit cycle, what is going to happen? In case of a limit cycle, this is not the case. In case of a limit cycle, the system is going to follow that particular periodic orbit and it will not depend upon the initial state of the system. Like for example, for a limit cycle, if in a phase plane there is some limit cycle. Let us suppose this is a limit cycle. This is your x, this is your x dot. Okay, so I'll just change the color. Let us take green. So for example, I perturb it from here. This is my initial condition. What is going to happen? It is going to circle like this and finally attain this limit cycle and will start following this limit cycle. Okay, Now what if I give it some another initial condition? Let me take red. Inside the limit cycle, then it is going to go like this and it will again start following the limit cycle like this. Okay, so this is what a limit cycle is. Okay, as you can see that if I am changing my initial condition, the orbit that the system is following is the same. Okay, the orbit is not changing, correct? So this is what is the difference between a limit cycle and that of a periodic oscillation. And that is why we say the limit cycle as an isolated periodic orbit. Okay, now coming on to existence of closed orbit. So by some numerical behavior or by looking at the equations, see now since we have dealt with many equations and we are still dealing with some equations. So if you keep on dealing with these equation, you get an intuition that okay, it may happen that this kind of a system is not going to have a closed orbit. Okay, so how do I know? So some techniques were discussed by which we can see whether there will be a closed orbit in the system or not. So like in the gradient system, it was shown that if my equation of motion is given as x dot and y dot, and if now I can write these x dot y dot in terms of a gradient function, then in that case it is not going to have a closed orbit. Likewise, there was this Dulac criteria and Lyapunov function by which we could tell that whether my system is going to have a closed orbit or not. By this we can actually see if my system has a closed orbit or not. See, for in a practical case, if I require that my system should have a closed orbit. So by these criteria, I can check that the system is going to have it or not. There is no point of doing iterative simulations and finding out the closed orbit if it is not even having a closed orbit. The equation of motion is in such form that it can never have a closed orbit. Then it is better that we do these tests and then proceed with the further work. Okay. So likewise, these three systems were discussed. Then stability and bifurcation of periodic response were discussed. Now, by stability of periodic response, what we mean is it's like, see, we were discussing for in the last weeks live session, we were discussing about the stability of a particular fixed point, like what and how were we predicting whether it is a stable fixed point or an unstable fixed point. Well, like we were giving some oscillation, some perturbation we were giving from the fixed point, and if with time it was coming back to the fixed point, then we were saying that it is a stable fixed point. If it was going to infinity with time, we were saying that it was an unstable fixed point. Right. Likewise, we can say for a periodic response also, like if the system is following a periodic cycle, if it is following a periodic oscillation, and I will give a very small perturbation initially from that path, and if it again comes to that cycle, then it is stable. If it goes away, it is unstable. Simple. Same analogy we can say that it follows. Now coming on to the bifurcation of periodic response. So like in case of a fixed point, we saw that there are various kind of bifurcations. Like we had pitchfork bifurcation, we had saddle node bifurcation, we had transcritical bifurcation, wherein the characteristics of the fixed point were changing. Right. So similar kind of behavior can also occur in case of a periodic response. Okay. Bifurcation essentially means the change in the stability or change in the quantity of the periodic response. Like for example, we had one periodic orbit, but after the change of the parameter, now there are two periodic orbits, or there is an orbit which has time period twice of that of the initial periodic orbit. So this in this way we can say about the bifurcation of the periodic response. Okay, so it can be due to the change in the number of the solution, or it can be depending upon the stability of the solution. Okay. It can be of change in the number of solution, or it could be about the stability of the solution. Okay, these two things can occur. And at last, chaotic response was discussed. So it was discussed about that what chaos is and what are the properties that a chaotic response shows, and the systems that show chaotic vibration, and what are the route to chaos, how are we actually reaching to chaos, how the bifurcation is actually taking place that leads to chaos, and every these kind of things were discussed. Okay, so this was it about the overview. I hope that you people have gone through the lecture, so I'm not discussing it in a very like elaborate manner. I'm taking it very briefly, and if you have any doubt, you can ask in the live session. Okay, in between also you can ask. So I'll start taking up the questions now. Okay. Okay, so the first question says that for a system with the Floquet multiplier leaves through -1, that which type of bifurcation occur? Okay, so first thing first, that what is a Floquet multiplier? Where is it coming from? Although I have discussed it in the previous session and it was discussed very thoroughly in the previous week's lecture also, but I'll still give a brief and then tell you. So talking about a Floquet multiplier, so if you remember that what were we doing? We were actually linearizing the system. We were actually linearizing the system about uh, already known solution, and after we were linearizing it, we came to know that we can write a relation in a way that your u1 at t plus tau and u2 at t plus capital T is equals to a matrix into u1 at t and u2 at t. So if you remember that this was for a parametrically excited system. So I hope you people know what is a parametrically excited system. A parametrically excited system is a system wherein our parameters, the parameters that are in the equation of motion, are actually changing with time. Okay, and we say that this parameter variation, for this we have t as the, I'll write it here. Your t is the time period of parametric excitation. Okay, so if you have your small t, you know the response at small t, u1 and u2, and you want to know that what would be the response at t plus capital T after one time period. What is the response of the system after one time period? Okay, so this is how we can write it. We obtained it by linearizing. Okay, so there is a way by which we can actually get the value of this variables aii, that ij, that I have used in this matrix. And so for example, if I know the equation of motion of a system, okay, and I want to know this matrix, so that by this matrix only, if you remember, by finding the eigenvalues of this matrix only, we were actually predicting whether my system is stable, unstable, or whatever can happen. Do you remember? We were actually evaluating the eigenvalues, and then eigenvalues, I'll just write eigenvalues of this matrix tells about the stability. So if you remember that we had this real axis, we had imaginary axis, and then we had a unit circle. So we told that if my lambda is going to lie inside the unit circle, then my system is stable. And if lambda lies outside the unit circle, then my system is unstable. Right? We were using that technique only. You remember we had this kind of a relation wherein u of t plus nt is equals to lambda to the power nt. Yeah, this was the relation as far as I remember. This was how we were writing about the equation. So essentially we knew that the behavior is going to change like this. It is changing by lambda to the power n. So if my lambda is greater than 1, then my system is unstable, because you see something which is greater than 1 and its power gets increasing, its power is increasing. So what is going to happen? It is going to become a very large number. Right. And if my lambda is less than 1, then my system is stable. Uh, Whatever I'm writing, it is getting updated, or is there any lag with my voice and writing? Okay, fine. I suppose it is okay. Okay, so this is what it is. Okay, so by this we were actually telling, okay, thank you. So by this we were actually telling about the stability of my system. Now, if you people remember, then there was this case when we were actually writing something like we had four like initial condition in this way, like we had u at 0 was equal to 1, u0 was equal to 0, u2 at 0 was equal to 0, and u2 dot at 0 was equal to 1. Remember, if we take these initial conditions, we replace small t by 0, and after capital T, we can find the solution. Okay, so if I'm going to put this initial condition into this, what is going to happen? You will get to know that my u1 of, okay, I'll just do the mathematics very quickly. So u1 at t and u2 at t was equal to, we have a11, a12, a21, a22, 1 and 0. Okay, so if you see here, what you are going to get is that my a11 is equal to u1 of t, and my a21 is equal to u2 of t. Correct? Similarly, you are going to get that my a21 is equal to u1 dot of t, and my a22 is equal to u2 dot of t. So in this case, whatever this matrix A I get, it was being called as the monodromy matrix, right? So for a system, if I know the equation of motion, I know the initial conditions, what I can do is, and I by the seeing the parametric excitation, whatever is happening by the equation of motion, I can find out capital T, right, which is the time period of periodic parametric excitation. So if I know the time period, I can do the simulation and I can find whatever the system response is after a time period. Okay, and then I can find the monodromy matrix, and then by using the monodromy matrix, I can predict whether my system is stable or unstable. Okay, for that matter, if it is asking about that if the Floquet multiplier leaves through -1, which means is that we have a parameter. If you remember, in case of a bifurcation, we have a parameter which we vary with. Okay, and we see whatever the response of my system is. So if I have this parameter mu and I'm varying this parameter, okay, so it may have, it is going to have a critical value. Let us say mu c. I should write it. Mu c is going to be my critical value. So it may happen that for less than mu c, I'm going to have a different behavior. For greater than mu c, I'm going to have a very different behavior. And while crossing also, I can have a very different behavior. So based on the Floquet multiplier, or I should say the eigenvalues that I obtained from the monodromy matrix, I can tell that what kind of a bifurcation is actually occurring in my system. What I have to do? I just have to change mu. I have to take a very small value, less than mu, very small value added to mu, and by this I can see the variation which is near to mu and at mu c, and then I can see if it is passing through -1 or +1, how the system is going to behave. So if you remember that it was discussed in the class that what kind of a behavior is going to happen if my this is going to change. So if the Floquet multiplier, if my Floquet multiplier passes the unit circle, it is going to have three cases. If you remember, first case was my through +1. Okay, if it passes through +1. Now by +1 means +1 on the real axis. Okay, how are you going to see? You are going to see it by the monodromy matrix, vary the parameter and see how it is going to change. So if it passes through +1, then three type of bifurcation can occur in the system. What are those three types? First one is your cyclic fold. What do you mean by cyclic fold? So if you remember that there was this saddle node bifurcation. Okay, there was this saddle node bifurcation that was seen to happen in case of a fixed points. Okay, so in case of a saddle node bifurcation, what was happening? If you remember that there was this parameter mu, and then my point was like there was this stable fixed point, there was this unstable fixed point. They met at a point, and then after that there was no fixed point in the system, right? Similar kind of a behavior is present in this kind of a system. This is a dynamic bifurcation. That was a static bifurcation. Static because the change was from one fixed point to two fixed points, no fixed point to two fixed points. Anyways, we were dealing with the fixed points. Here we are not dealing with the fixed points. We are dealing actually with the periodic cycle. We are dealing with a periodic oscillation. So in case of a cyclic fold, what happens is that if I have my mu at the x-axis, which is my parameter, and then I have a amplitude. I'm plotting the amplitude. Okay, we can write any periodic behavior as a sine omega t plus phi, where a is my amplitude. So on the basis of this, I can know that what are the maximum minimum values that a system could reach. So I'm plotting the amplitude over it. So in case of a cyclic fold bifurcation, what is going to happen? Similar to the case of a saddle node bifurcation, there is going to be a unstable branch and a stable branch which would come, and its intersection is going to cause the destruction of the amplitudes. Okay, and this destruction would lead to existence of no further amplitudes, which means that there is no more periodic. Like if this is my mu c, right? So for less than mu c, I have two amplitudes. One is stable, one is unstable, which means that I have two periodic cycles. One is unstable and another one is stable. And as mu increases from mu c, the periodic cycle is going to vanish. There is no periodic cycle further. Okay, this was your cyclic fold bifurcation, right? Now there can be another case also, which is just symmetry breaking. Now there is this symmetry breaking bifurcation, wherein, as the name suggests, it is related something to symmetry. So if you remember that in case of static bifurcation, we had pitchfork bifurcation, right? Wherein there was this one fixed point, and then it was bifurcating into two further stable fixed points, and this one was becoming unstable, right? And we had another also. Okay, and then we had another case. So this was your supercritical pitchfork bifurcation, and there was this subcritical pitchfork bifurcation as well, wherein there was this zero here, like this. I had a unstable branch which bifurcated into two further unstable branch, and this previous unstable branch became stable. Okay, so these are the cases. So similar to this is the case of a symmetry breaking bifurcation. Now, in case of a symmetry breaking bifurcation, what actually happens is that initially I had a periodic cycle. C, let us say. Okay. Now, as the parameter varies, what is going to happen is it results into three. My C has now becomes unstable, and now I have two new cycles, C1 and C2, which is now stable. Okay. So what happened is that as the parameter was varied, my this C orbit, which is also periodic orbit, bifurcates into three further periodic orbits. Or I should say two orbits. C was already there. So now this C has become unstable and it results into two new orbits, C1 and C2, where my C1 and C2 are now stable. So if you see, this is related to that of a supercritical pitchfork bifurcation, right? So if I want to draw my amplitude versus parameter mu, how can I draw it? Let us say that this is the amplitude. I was having one amplitude which was increasing with mu, and at the point of bifurcation, which is my mu c, it led to the two further stable new cycles and one unstable one. Right. So this was my symmetry breaking, and this is, as you know, this is a super critical case. There can be a subcritical case as well, wherein what is going to happen if I have an amplitude and if I have a mu, what is going to happen? As the name suggests, subcritical, which means that there would be an unstable amplitude, which would further bifurcate into two new unstable amplitudes, and the previous unstable amplitude would become stable. So by that analogy, I can actually find it. Right, I can find out how it is behaving. So let us suppose that this is my orbit. This becomes stable, and this originates two new unstable amplitudes. Now, what is to be kept in mind while studying this is that all the values on the y-axis are actually amplitude of oscillations, right? So amplitude of oscillations are actually changing. Okay, and then there is going to be a third kind of a bifurcation as well, which is your transcritical bifurcation. I hope that you people remember that what the transcritical bifurcation is. There were two branches, one branch was unstable, other branch was stable, and after the critical parameter value, the stability reverses itself. Right. So if you remember that it was like, let us say this, and then there was this. And this is my mu c. This is mu and this is amplitude. Right. So what is happening with the parameter? There occurs a bifurcation at this point, after which this branch was initially stable. This branch was initially stable and it became unstable after mu c. And this branch, which was initially unstable, became stable after mu c. So this is a transcritical bifurcation, which means amplitude is varying. Now you can see that the analogy is same as that of a fixed, the bifurcation which is related to the fixed point. Now coming on to, like, see, if for this case we had that the Floquet multiplier passes the unit circle through +1. Now it can pass the unit circle through -1 as well. It can pass the unit circle by -1 as well. We have through -1. What kind of a bifurcation occurs? Period doubling bifurcation. It is a very interesting kind of a bifurcation. We have period doubling bifurcation. Now, what is a period doubling bifurcation? So, in case of a period doubling bifurcation, what happens is that, as the name suggests, that there is doubling of the period. Okay. So, initially there was this, let us say, orbit C. As mu is equal to mu C, let us say. Okay, let us do one thing. This is for mu less than mu C and for mu greater than mu C. What is going to happen is that there is something like this, C1. It is such that the period, if this was having a period T, it has a period of 2T. So as mu is equals to mu C, what happens is that C becomes unstable and a new periodic orbit with time period 2T appear. Okay, so this is what happens in case of a period doubling bifurcation. So initially there was this periodic orbit. Now as I changed the parameter, as mu was varied, this orbit C, it becomes unstable and a new orbit C1, which has a time period 2T, 2 into capital T, appears. So this is a period doubling bifurcation. So if my Floquet multiplier passes through -1 with the change of parameter, my period doubling kind of a bifurcation is seen. And third case is that of a, if it leaves unit circle away from real axis, which means if this is my unit circle, these are my two conjugates, they're leaving like this as mu is varied, then what kind of a bifurcation occurs? So it is also known as the secondary hop bifurcation. Okay, secondary hop bifurcation. What is the difference between a hop bifurcation and secondary hop bifurcation? So in case of a hop bifurcation, my fixed point was actually changing into a limit cycle. In case of a secondary hop bifurcation, it is not necessary that it is going to be a limit cycle. It may be a quasiperiodic or periodic orbit. Okay, so these are the things. Okay, so the question says, what is the question? Let me come to the question. For a system, if the Fokker multiplier leaves through -1, then which type of bifurcation occur? So you know now that period doubling kind of a bifurcation is going to occur. I hope that it is clear. Coming on to question number 2. The Poincare section of a periodic response can be. Okay, so firstly, what is a Poincare section? So it is actually what we do is we take a section from the response in order to reduce the dimension of the system. Now by dimension, I mean the physical dimension. So Poincare section is essentially a section which is taken out from the behavior that we know. Like if you remember, what do? We have an equation of motion. We simulate it by OD45. what do we get? We were getting its position, we were getting its velocity. Acceleration we don't need because we already have the expression of acceleration. Okay, the differential equation that I'm having is actually a like analytical form of the acceleration only, right? So if I already have the form of acceleration, so I'm using ODE45 to get the position and velocity. Okay, so I know that how the position and velocity are actually changing with time. Okay, but if I want to know that if I reduce a like dimension, I have that x is changing, I have x dot is changing, and I have t is also changing. So what if I want to create a section? Like in case of a three-dimensional plot, we try to take a section. We take a plane and we get a sectional view. Like what is the behavior of the system on the particular plane? So for that case, we collect the Poincare section. Now in the case that we are discussing, and it was discussed in the class as well, that if we have a forcing of omega, and so we have time period is 2 pi by omega. Okay, and I have the system response. So what was I doing? I was taking the sections after every time period, right? So if I had x dot, I had a data of x and x dot. Okay, now I am cutting this after every time period. Like I have this. Sorry, let us suppose that these are my datas. I have n number of data for corresponding to each timestamp. These are the timestamp. But I want to filter out. I want to filter out the time, the response at the time after every time period. Like for example, I took the response at t is equals to 0. Then I took the response at t is equals to capital T. Then I took the response at t is equals to, this is for this is for a t is equals to 0. This is for a t is equals to capital T. This is for a t is equals to 2 times of t. Okay, so this is how I am taking out the response. So whatever the data that I get after taking these responses out of all the data I have is what, and then I plotted is what I call as a Poincare section, right? So if I talk about a periodic response, like let us suppose that for a linear spring mass system, what am I going to get if I have a periodic orbit? Okay, and we know that for a if I have damping present in the system, the dominating effect is going to be that of the forcing function, and the forcing has a frequency of omega. So definitely the time period of oscillation is 2 pi by omega, isn't it? Because for a linear spring mass system, I can have two presence of two kind of a frequencies. One is a natural frequency and second one is the frequency due to the forcing. Because the system has damping in it, the whatever the behavior which is due to the natural frequency is going to die down with time because of presence of the damping. So whatever is going to remain, will be because of the presence of the forcing. So if I have t is equals to 2 pi by omega, and I see that for a periodic response, if I try to plot a Poincare section, it is going to be a point, just a point. Here like this. This is here my Poincare section. How? Because see, at t is equals to 0, this is where the system was, right? After one time period, what is going to happen? It is going to go like this, and it is going to be at that point only, isn't it? Do you people know about the stroboscopic effect? It means that if we, whatever the vibrating system is, if it is vibrating at a certain frequency, and then I am trying to provide it light only at that particular frequency, I'll see that the object, though it is vibrating, it appears to be static. Similar is this case. I'm actually taking the response whatever after one time period. And after one time period, since it's a periodic behavior, it is going to be at that particular point itself after one time period. Right? Because it is a periodic response. So it is going to be a point. Now, what if a period doubling kind of a bifurcation occurs? So as you know, in case of a period doubling bifurcation, this is going to change like something like this. This is after period doubling. Okay, so after period doubling, this is how the phase plot looks like. I should make axis so that it becomes clear. Okay, so this is how it would look like. So if this is how the phase plotted, and we know that after period doubling, what happens? My time period becomes twice of t. That is what I discussed here. In case of a period doubling bifurcation, C becomes unstable and a new periodic orbit with time period 2t appears. So now this has a time period of 2t. So what is going to happen? If I take the Poincare section, see if I start from here, okay, this is at t is equals to 0. Now it will start covering like this. Now let us say that this is what the point that I get at t is equals to capital T, and then again it travels like this, and this is what I get at 2t. Do you understand what I'm trying to say? Now, since the period of oscillations has doubled itself, initially it was capital T, now it has become twice of capital T. So, and I'm cutting the section at every T, capital T. So at T is equals to 0, I got this point, right? After T, one time period, I got this point. And after one more T, I got again this point. So this is showing how the Poincare section is changing. So for a periodic orbit, it is a point. For a periodic orbit which occurs after period doubling, the Poincare section is 2 point. Right. Now, if I talk about one more period doubling, if it happens after this, what is going to happen? See, period doubling always changes with 2 to the power something. Okay, so if I would say that now 3 times of the t is going to happen, that is not the case. First it was t, then it became 2t, now it would be 4t. This how it is happening, and that I'll discuss in the other question, coming question. For now, it is going to have 4t. Now it is going to have 4 loops, let us say something like this. Okay, this is your x, this is your x dot. So now this case, if there are 4 loops, there's another period doubling that has occurred after this. So I'm going to have how many points in the Poincare section? 4, definitely. 4 times of the time period it is having now. This would be at t is equals to 0. T is equals to 4 times of t. Okay, so this is how it is. So the question says that the Poincare section of a periodic response it can be 1 point, it can be 2 point, it can be 4 point. So all the 3 options are correct. Because in all the 3 cases, the response is periodic. Although it is having different time period, but these are periodic. The response is periodic. Okay, so all the 3 options are correct. Coming on to question number 3. So the question number 3 says that the Poincare section of a chaotic response can be closed loop, single point, random points, none. So single point cannot be a correct answer because we know that for single point, it occurs only in case of periodic response. So if you remember that it was taught in your class that for a response, for a quasi-periodic response, if I try to plot the Poincare section, then it becomes a closed loop. It is a closed loop that I can see, right? So in case of a quasi-periodic response, the Poincare section is a closed loop. Okay, for a quasi-periodic response, the Poincare section is a closed loop. So anyways, this is not going to be our option B. Will like okay, I just give a brief about quasi-periodic response. Quasi-periodic response, you can, as you remember, it is going to have something of this kind, a torus kind of a phase plot, and its Poincare section would be something like this, a circle. If you take the points at every time, it is going to be a circle. Anyways, any closed loop, not particularly circle, it can have any of the closed loop, right? So closed loop is also not a correct option. So the third comes the random points, which is true also, because if you see that in case of a periodic response, if I talk about Poincare section, it is essentially talking about the periodicity of a response, isn't it? It was single point for a periodic response, which means that the response is periodic, right? 2 points for 2 period. Anyways, it was finite number of points for a periodic response. For a quasi-periodic response, it was more than a finite number, but it was actually making a closed loop, right? But because there was some relation, there is some relation within the periodicity, right? But in case of a chaotic response, which is also known as an aperiodic response, in case of an aperiodic response, what is going to happen? There is no periodicity present in the system, which means that my Poincare section is supposed to be some random points, right? If I talk about a chaotic response, it is something like if I plot time and x, it is going to be something like this, random, no particular behavior, random points. So if I take its section, if I try to take the section at every time interval, let us say like this, this was at capital T, 3t, 4t, 5t. Can you see this point, then we have this point, this point, this point. Can you see what is actually happening? These are all random points, and if I plot it now in the phase plane, it is going to be some random points, random distribution of points, isn't it? Because see, there is no periodicity. Like in case of a periodic system, I was having the behavior like this. I was always cutting it here. I was always getting the same point. But in this case, that is not what we are getting. We are getting random points. Sorry. And that is the reason that that a chaotic response is going to show random points. However, there is one thing that I would like to mention over here is that it is not necessary that always the random points shows the existence of chaos. You're going to study it further that if my system has damping present in it, then my this Poincare section is going to show me the presence of an attractor known as the strange attractor. Okay, so if in any question you have something like that, the Poincare section of a chaotic response can be random points or strange attractor. So both are going to be the correct option, provided if it is not mentioned that whether there is a presence of damping or not. Because in this case, your random points is the correct response, but strange attractor could also be a correct option. However, you people have not been taught about strange attractor yet, so we'll keep that thing untouched and we'll discuss it whenever it comes in the course. Okay, coming on to question number 4. This is a very easy question. I will not discuss anything because I've discussed it already. Secondary Hopf bifurcation may be observed if the Floquet multiplier leaves the unit circle through complex conjugate away from the axis. As I've discussed earlier also, that there were 3 cases. One, it leaves through +1, then we could have 3 kinds of bifurcation where we had the symmetry breaking, transcritical, and cyclic fold. And if it leaves through -1, We had period doubling bifurcation, and if it leaves the unit circle away from the axis, it should be real axis, then it is going to have secondary hop, or also it is known as the Nyman bifurcation. Nyman, yes, that was correct. Okay, so this is what it is. Now coming on to question number 5. Okay, the intermittency of chaos in the system response may lead to chaos. Okay, so what is intermittency of chaos? What is intermittency mean in case of chaotic response? Okay, so it comes from the word intermittent. I hope that you people are aware what does intermittent mean. So when we talk about intermittent chaos, what it actually means is, firstly, what is chaos? It is a periodic response, some random response. So for example, if I have the plot of x versus t like this, chaotic. Okay. Uh, should I say first I'll take periodic. Okay. If my response is periodic, would be something like this. Periodic. Now, if I talk about chaotic, random. This is my chaotic response. This is periodic. This is chaotic. So, see, if this is my periodic response for some parameter, let us say mu, and if I start increasing, mu is increased. Okay, mu starts increasing. What is going to happen? Intuitively, if mu is increasing, then maybe either the oscillation amplitude can reduce, frequency can increase, frequency can reduce, the oscillation amplitude can increase also. Whatever. Let us take the case where the oscillation amplitude increases. So if my oscillation amplitude is increasing with mu, what can I see that amplitude may increase up to a further point. Bifurcation can occur. Period doubling can occur. But is the period doubling only thing that leads to chaos? Not necessary. It may happen that with the increment of this amplitude, there is a sudden burst of chaos. Okay, like we humans also, if we have a very lot of work pressure, it may happen that we burst out. Okay, we don't know what to do. How should we solve every problem? It happens. It's natural. And I guess chaos and nonlinear dynamics is one of the best topic which would relate to how actually things are happening in the nature. So it may happen that there is an increment of amplitude keeps on increasing, and for a certain time chaos may occur for a very small time. So how can the behavior be then? The behavior would be something like my response is periodic. Now it has gone into chaos. And after some time, it again becomes periodic. So what do I see? I see that with the increment of time, my system was initially periodic, chaotic, periodic. So my system was initially periodic. With the increment of time, it had a sudden burst of chaos, right? And it then again became periodic. So this kind of a behavior is known as intermittent chaos. Okay, so in between some of the periodic behavior, it is showing some chaotic behavior. Now, this periodic behavior is not necessary to be of single period. It can be of two period or any kind of a periodic behavior, but it should be periodic. And there's a sudden burst of chaos for a very small interval of time. Now, how would I know that what could be this interval of time? Will the chaos occur again with time? And will the interval be the same? So these things are not, we cannot tell. Okay, if my system is having chaos, it may happen that after certain time it is going to have again a burst of chaos. Okay, but after how much time and for how much interval, we don't know. But what I know is that if I keep increasing my parameter mu, like for certain parameter mu, I saw that there is a burst of chaos for a very small time. But if I keep increasing the value of mu, this number of bursts that have been occurring, increasing, it starts increasing. Okay, so what is actually happening is, let me just write it. So initially, over a certain value of mu, response is periodic. However, as mu greater than mu c, a burst of chaos may be observed. Okay, as I said, that there would be a burst of chaos. Now, as mu increases further, the occurrence of chaotic burst becomes more frequent, right? It becomes more frequent. The burst would start increasing. The number of times it is occurring increases, and it may happen that the time for which it is occurring also increases, right? So if I know that for increasing mu, the burst increases, it becomes more frequent, what is going to happen? There will come a time when this is going to supersede the periodic behavior, and at the end, only chaos is going to be present. Okay, this may further lead to chaotic behavior of the system. Okay, so what I know is that if there is some intermittent chaos with the increase of parameter, it may happen, and if I further start increasing mu, the intermittent chaos or the burst of chaos starts occurring more frequently, then it is going to lead to the chaos, right? So, as the question says, the intermittency of chaos in the system response may lead to chaos. The answer would be yes. However, there are two, three things I would like to discuss over here is that I've discussed about the intermittency of chaos, and this is also known as the, sorry, this is also known as the intermittent route to chaos. However, there are two more routes which would lead to chaos. First one is your period doubling route. No, this would be my second. First one was this. Second is my period doubling route to chaos, which I have discussed briefly also. Period doubling, what was happening? With the change of parameter, my time period was doubling itself. Okay, so in case of a period doubling, what is going to happen is that for, let us say, mu, some mu, which is less than mu c1. Okay, I'm going to have that response is a periodic orbit with time period t. Now, as soon as my mu increases from mu c1, if my mu is greater than mu c1 and less than mu c2, what is going to happen? My response will be a periodic orbit with time period 2t, right? And now, if my mu is greater than mu2 and less than, mu c2 and mu c3, my response would be periodic with time period 4t. So this is my period doubling kind of bifurcation. And this, when it starts increasing, no, so if there will come a situation, usually we consider it after 16 number, I guess, that there will be so much presence of so many periodic elements that it would become aperiodic. Okay, and it would lead to chaos. So in this case, generally we can write that periodic with T, okay, where my K could be. Okay, so this is my, in general, we can write it like this. Now, period is going to double it like this, right? And this may lead to your period doubling bifurcation, which would further result into chaos. So this is my period doubling route to chaos. I hope that you people are able to understand what I'm trying to say. See, talking about this is easy, but if you try doing this, like Sir has also taken an example and explained how period doubling is actually occurring. Actually, I'll also take an example and I try to write that, show you through simulation that how it is actually happening, period doubling. So this is how it is. Okay, your time period is going to change like this with K, where K is going to be your critical, like, number of times the critical parameter is occurring. Like for example, if I have a mu C1, then the time period is going to change with from T to capital T, right? So this is how it is going to happen, right? Now, these are the two routes. There can be a third route also, which is your quasi-periodic route. Quasi-periodicity can also be seen. I'll just write. There could be a quasi-periodic route also. So in this case, hop bifurcation may occur. Hop bifurcation may lead to your periodic cycle, and then there can be another hop bifurcation which may lead to a periodic cycle with double of the this which may lead to double of the time period. And like if there are presence of two different periodic orbits which have their frequency ratio as irrational. If you remember that for a quasi-periodic response, if there are two frequencies whose ratio is irrational, or we can also say that the two frequencies are incommensurate, then in that case quasi-periodicity happens. If there are two periodic orbits whose frequencies are incommensurate, then in that case it may lead to quasi-periodicity, and then this further enhancement would lead to your chaos. Okay, so there can be quasi-periodic root. There are three roots which may lead to chaos. So the answer is, I guess, clear. Coming on to question number 6. So for the system given as this, which type of bifurcation occur at origin? Now, if you remember that for which kind of bifurcation, the best way is that I calculate the Jacobian, right? So first I'll try to calculate the Jacobian. What is going to be my Jacobian? So Jacobian was, if my x dot is equals to f of x comma y, and y dot was f2 of f1 x comma y. So my Jacobian could be given as del f1 by del x, del f1 by del y, del f2 by del x, and del f2 by del y. So this was my Jacobian, right? So now if I try to find out that what is the Jacobian, so it would be, if I differentiate, first your f1 is being differentiated with respect to x. So you can see, now maybe I should write it. Now this is a very simple differentiation, so I'm not covering much. Mu. Now the first thing is that it says that origin. It has mentioned specifically origin. So now I can put 0, comma 0 in the Jacobian. So uh, this gave my Jacobian at x comma y, at some random x comma y, and I can find Jacobian at 0, comma 0 as mu minus 1, 1, and mu. So if I want to find the eigenvalues, because on the basis of eigenvalues only I can tell that which kind of a bifurcation can occur. I can tell about the stability, and then I can talk about the bifurcation. Right. So if I want to know that which kind of a bifurcation occurs, so if I want to find the Jacobian, I would have to find the determinant of G minus lambda I, which would be mu minus lambda whole square plus 1 is equals to 0. I hope that this is clear from where I'm getting. So mu minus lambda square, okay, I'll just, from which I have mu minus lambda is equals to plus minus of I, because under root of minus 1 is I iota. So I have lambda is equals to mu plus minus I. This is my eigenvalue. Correct. Let me check also. Yes, lambda is equals to mu plus minus I. Okay. Now, if you see that my origin, what is its stability? So if my mu is less than 0, what can you see? The presence of minus I means that there is going to be a circle. there is going to be a circle. Either it is going to be a constant circle, it is going to spiral in, spiral out, and that would depend upon the value of mu. So if my mu is less than 0, my lambda is going to be a complex number with a negative real part. Negative real part means that it is going to spiral in. So for mu less than 0, my origin is a stable fixed point. Simple. And if my mu is greater than 0, then my origin is an unstable fixed point. Okay, so my origin is stable for mu less than 1, for greater than 1 it is unstable. Now if I talk about mu is equals to 0, I see that my lambda is equals to plus minus 1. If you see, it means that there is going to be a periodic orbit, right? And the periodic orbit is going to have omega as 1, correct? So if this is a periodic orbit, how the system is going to behave? So if I remember, I hope that you people also remember that there was the some conditions that were discussed in I don't remember the exact week, but it was discussed that depending upon the function that has been given, I can tell whether what kind of a bifurcation is occurring in the system. So since lambda, see, uh, if I talk about bifurcation, it was of two types, right? One was my static dynamic. I mean, essentially bifurcation was a two type, continuous and discontinuous. So under the continuous, there was static and dynamic. So in case of a static, we had our saddle node, then we had pitchfork, we also had transcritical. Right, these were the three we were having. But in case of a dynamic, we had a hop bifurcation. If you remember, there was this hop bifurcation. So was what I remember was that in case of a if I'm saying static bifurcation, it means that there is a change of fixed point. There was a fixed point and there were variation. Either it was a stable fixed point, it was an unstable fixed point, it was coming to the fixed point by the exponential function, it was coming to the fixed point with some spiraling in, it was going away with the fixed point with exponentially, then it was going away from the fixed point in spiraling out behavior. Anyways, it was something related to the fixed point. In case of a dynamic of bifurcation, I know that there is some dynamic behavior, which means that there is the presence of a periodic orbit, right? So I can see that for mu is equals to 0, I have plus minus I, which means that there is a periodic cycle. So it may happen that it is a Hopf bifurcation. So I now recall the conditions that were given to know whether the bifurcation that is occurring is a Hopf bifurcation or not. So if I talk about first, if you remember the conditions for Hopf bifurcation, the first condition was that f of your, I guess, x naught and that parameter mu c should be equal to 0. This was your first condition. So if I see my equation, I have two equations. This is my f1 and this is my f2. Right. If I see f and I know that my this x naught, which is my fixed point, is actually origin, which is x is equals to 0 and y is equals to 0, and my mu is also equal to 0. Right. My critical mu is 0. Right. I hope you know this. This is a very easy From where do I get it? I get it from this only, from this eigenvalue, because mu is actually changing behavior at mu is equals to 0. Before mu is equal to 0, it was stable. After mu is equals to 0, it is unstable. So mu c, my mu critical value is 0 itself. So if I put x naught, which is 0 comma 0, and if I put mu c is also is equal to 0, I'm going to get both f1 and f2 are equal to 0. You can see it from the equation also. See, I'm going to get 0. So my first condition is satisfied, right? My first condition is satisfied. Coming on to the second condition. My second condition says that my Jacobian, which is d of x of f, which is essentially the Jacobian, it should have pair of imaginary eigenvalue. And depending upon the number of real part, imaginary part, and zero non-zero part, it was uh, uh, I don't remember the word as of now. Anyways, so this Jacobian has a pair of imaginary eigenvalue. Yes, I have a pair of imaginary eigenvalue. See, my Jacobian is having pair of imaginary value. So my second condition is also satisfied. Now comes the third condition. Third condition says that when mu is equals to mu c, your if your eigenvalue is written like what would I say? A plus IB, then your del A by del mu should not be equal to 0. Del A by del mu should not be equal to 0. That means your real part of the eigenvalue should not be equal to 0 if it is differentiated with respect to mu. So if you see, my real part of eigenvalue is mu itself. So if I differentiate mu with respect to mu, what do I get? 1, which is not equal to 0. Which means that my third condition is also satisfied. And this third condition also says that if this is the case, then there is a periodic response at mu is equals to mu c. Yes, I am getting a periodic response because my eigenvalues are plus minus iota, right? So yes, these three conditions are satisfied, which means that this is a Hopf bifurcation. This is a Hopf bifurcation. However, Hopf bifurcation are further of three types. It could be subcritical, it could be supercritical, or it could be degenerative as well. So how do I know? So now the only way that I can know is simulation, right? Analytically, I could do this, but now differentiating between different kinds of Hopf bifurcation, I had to have to do some numerical simulation so that I can understand how it is happening. Okay, so now I'll switch to my laptop to show the MATLAB simulation. Okay, so is my screen visible?
Yes, madam.
Okay, thank you. Okay, so let us come to the equation. I'll just open the PPT as well. So this was my question, right? So this is mu x minus y plus x y square. So if you remember, for a two-dimensional system, I'll define my x as z of 1 and I'll define my y as z of 2, and then I'll write it into the code like this. So first equation is mu into x minus y plus x into y square, and my second equation is written like x plus mu y plus y cube, which was given. So I have taken this, and now I have taken mu as minus 0.2. See, my mu critical was 0, right? So first I'll do one thing. I'll just take mu as plus 0.2, and then I'll just simulate. Let us see what happens. And I've taken the initial displacement as 0.64. Okay, let me simulate now. Did you see what happens? It is showing that failure. System is failing, which actually means is that the velocity of the system with time is increasing like this in a vertical, very abruptly. So now MATLAB has stopped the simulation. Usually, if there is an abrupt change in the system behavior, MATLAB stops the simulation. Okay, so see here, the velocity is changing. Okay, I should maybe write the labels so that it would be easier. So I'll add X label time, Y label as position. Now let us see. Now see. So if you can see. Now how do I know it is increasing with time? So see, with time, my position is going from around 0.65 to 1.6. So here with time, from 0.65 to 1, yeah, sorry, 0.1. At 1.6, it is going to around 0.1. At 0.1, you can see that the velocity has now is now increasing vertically, right? Which means that the system is unstable. Even a small perturbation is taking it to infinity. Now, what if I take 0, 0? If I know that my 0, 0 is an unstable fixed point. Unstable means if I am starting from that fixed point, it is always going to remain at that fixed point. But if I am going to give a very small perturbation, it is going to go away. See here. See. If my position is 0, 0, it is remaining at 0, 0. It will remain like this for infinite time. Okay. But if I give it 0.001, very small perturbation, let us see what happens. See, see. With time, the position is going to infinity, that too vertically. So the system is unstable. Okay, fine. Whatever I did analytically, that for mu greater than 0, my 0, 0 was unstable. Okay. Now, also there is one thing that as mu, see, there were two kind of bifurcations, Hop bifurcation. One was your supercritical and another was subcritical. So if you remember that for supercritical Hop bifurcation, when my zero was getting unstable, there were two new periodic orbits that were coming into the system response, which were stable, which were stable. That is, if there were any kind of a periodic response with the increment of mu, it could actually go into that loop. But what you are seeing is that it is going to infinity. It is not coming in contact to any of the stable response, which means that this is not a case of a supercritical Hopf bifurcation. So what is left? Subcritical. Yes, it is a subcritical Hop bifurcation, but let us just see also that how it is subcritical hop bifurcation. So this is not supercritical. I hope that it is clear. Now coming on to subcritical. Subcritical means that initially there was this unstable set of periodic solutions and my zero was stable. Zero was stable and then there were two unstable solution and then they were merging and they would lead to zero as unstable, which is true. Zero is unstable and for less than mu, let us just see. So I took mu as 0.02. Let us run the simulation. What do you see? So here you can see that as I gave it this initial condition, it showed some oscillatory behavior, or I should say spiral in behavior, and it reached zero. So when zero is a stable fixed point, right? Zero is a stable fixed point, but is it always stable? Now I know that it would result into a, okay, I think I mentioned something wrong. I said that in supercritical Hopf bifurcation there are two. No, see, that was in the symmetry breaking. Sorry, in the symmetry breaking we were having two periodic this solutions. In case of Hopf bifurcation, subcritical Hopf bifurcation, I had a fixed point and it would result into a limit cycle, a stable limit cycle, right? A stable limit cycle. I had zero as stable, and then it would, after the critical point, I crossed the critical parameter value, it would result in the stable limit cycle and an unstable fixed point. While in case of subcritical Hopf bifurcation, I would have an unstable limit cycle with stable zero, and it would lead to, the limit cycle would vanish, obviously, and it would lead to zero, also results in instability, right? So here you can see that it is spiraling into zero. For initial condition 0.64. Now it is very important to notice that there is a limit cycle. Obviously, if it is subcritical, then there is a limit cycle which is unstable, right? So what if I give it a perturbation which goes out of the limit cycle? It can never reach a limit cycle. Limit cycle is not going to attract it towards itself. So what is going to happen? It is going to throw to infinity. So now I try to find out. Let us change it to very small. Well, let us give a very small change. Let us take it as 0.65. Now let us simulate. See. Now you can see that now my response is going to infinity with time. This means that yes, there is a subcritical Hopf bifurcation. If my initial condition is inside the limit cycle, inside the unstable limit cycle, then it would take my system to the response to the fixed point 0, 0. However, if my initial condition is outside of the unstable limit cycle, it would take my system to infinity because the limit cycle is unstable. It is never going to catch hold and bring it back to the limit cycle. Neither it is going to catch hold and bring it back to zero because in between we have an unstable limit cycle, right? So it would go to infinity. So this shows that how my system is actually behaving and what kind of a Hopf bifurcation is actually happening. So initially we did some analytical analysis and then we did some simulation. However, you can also go to simulation, however, to see what kind of a bifurcation is occurring. But see, since we already did analytically, we knew that there is a Hopf bifurcation. Now we know that there is a Hopf bifurcation, then it was really easy for us to know that it is supercritical or subcritical. Okay, so the answer of this question would be subcritical Hopf bifurcation. Okay, coming on to question number 7. So for the van der Pol oscillator, the equation is given. Which of the following is correct? Limit cycle oscillation exists for mu 6. Limit cycle oscillation exists for mu 0.1. So let us take one by one and let us see what is happening. So first is for mu 6 we have to see. So see, I have already written the code like this. So here is the equation. So we have mu I have taken as EP. So let us take EP as 6 and I've taken the initial condition as 2, comma 0. Let us just simulate. Okay, I should again add uh, okay. Now let us simulate. Now see, if you see these plots, you're going to understand. See. So first is your position with time. You can see that this is how the position is varying, right? Then you have position and velocity, and then you have velocity and time. So if you remember, there were two things that was discussed in the lectures. One was the limit cycle, and another was the relaxation oscillation. So a limit cycle is essentially somewhat of the shape of a circle or ellipse. And when this ellipse distorts with the change of parameter, no, so it would result into relaxation oscillation. Okay, so why do we call it as relaxation oscillation? So what happens is that in this kind of a system, if you see the velocity variation with time, see here, the velocity over here is varying very slowly. However, after this, the velocity change is very abrupt. It is very abrupt. It is almost vertical. Okay, so in a very infinitesimal time, it is changing a lot. After that, it again has a variation which is slow, which can be seen by this curve. And after this, it again has the variation as abrupt. So this is known as a relaxation cycle, which means that here the system relaxes and then here the system jumps. Then again it relaxes, then again it jumps. Okay, so this is known as the relaxation oscillation. You can consider or you can have an explanation from here also. Here you can see that the velocity is changing almost in a horizontal fashion, right? Horizontal fashion means that the change in velocity is very less for a very big change in position. You can say that the slope is very small, right? The variation of velocity with position is very small. However, if you consider the behavior here, you can see that the variation of position is very small. However, the velocity changes very abruptly. So here the system relaxes, here the system jumps. So this is why we call it a relaxation cycle. So it is also said that in this kind of a case, the system has two like time scales. One is a very fast time scale in which the system jumps, and one is a very slow time scale wherein the system behaves in a relaxed manner. Okay, so this is known as a relaxation oscillation, and it is different from that of a limit cycle. I mean, not different. This is also a limit cycle essentially, but it is a limit cycle with a different shape and different kind of a behavior. But this is also a limit cycle. This is also going to show limit cycle behavior. See, if I change the initial condition, like it was initially 2, I would change it maybe to 10. See, even if the initial condition was very away from that of the cycle, see again it has come to the same phase plot. However, there is a phase difference, not considering the phase difference in time and the position and velocity variation with time. If we consider this phase plot, it is the same, right? In the steady state, after if we like don't consider the transient, we'll consider from here maybe 8.33, then the phase plot is going to be the same. So your first option is not correct. Your first option says that limit cycle oscillation exists for mu 6. This is not correct. So limit cycle oscillation exists for mu is equals to 0.1. Let us see. Let us change mu to, let us change mu to 0.1. Now let us simulate, see what happens. See, now if you see the variation, you can see that it is a somewhat elliptic cycle, and hence this is my limit cycle. So yes, for mu 0.1, my system is showing a limit cycle. How do I know this is a limit cycle? So let us just take some other initial condition also. 0.2, let us say. So 0.2. See, it is going to follow the same orbit, right? So this is a limit cycle. Now coming on to option C. So my option B is correct, right? For mu 0.1, I have a limit cycle. Right, if I talk about option C, relaxation oscillation exists for mu 8. Let us take mu as 8 and then simulate. Now see, if you see, is it a relaxation cycle? Yes, it is a relaxation cycle, isn't it? See the variation here, the velocity varies slowly, then changes abruptly, varies slowly, then changes abruptly, varies slowly, then changes abruptly. Similar can be seen in the phase plot as well, that the velocity variation here is very small as compared to the position, and here the variation is very large as compared to the change in position. So yes, this is a relaxation cycle. So your option C is also correct. The option C is also a correct option. Now fourth one is relaxation cycle exists for mu 0.5. Okay, I'll just show you this. However, I hope that if you have gone through the lectures, you already know that for 0.5 it is going to be a limit cycle and not a relaxation cycle, because for van der Pol equation, if my this mu is greater than 1, very greater than 1, then I'm going to have a relaxation cycle. However, if my mu is less than 1, then I'm going to have a limit cycle, right? See, this is a limit cycle. It is a distorted ellipse. Okay, the variation of velocity is somewhat sinusoidal. It is sinusoidal, right? There is no abrupt and slow change kind of a thing. Let us change the initial condition as well and see what happens. See, so there is some phase difference, but the phase velocity is the same. So my option D is incorrect. Okay, so I hope that it is clear. Now coming on to question number 8. Check whether chaos may occur in which of the following system. See, this question I have taken, I hope I will not discuss one by one every option, because I think now you people have become familiar with MATLAB and how to solve the equations. Okay, so what do you have to do is, you have the equations, you can put it in MATLAB and then see that whether chaos is actually present in the system or not. However, if you see intuitively that these systems have stiffness parameter as positive, then the parameter for x cube, coefficient of x cube is also positive, and the forcing is very weak. If you remember that we studied about uh, weak forcing and strong forcing. Remember weak non-linear or strong non-linear. So it was like when we compare it with this, the coefficient of x or our omega n square. So compared to that, if the coefficient of forcing, if it is very small or if it is comparable with that value, then I say that it is a strong forcing. And if it is not comparable, it is very small, then we say it is a weak forcing. So if my system is having a weak forcing, and then after that it is my strain stiffening system, stiff, or should I say hardening system, right? Because I have 2x plus x cube. As x increases, my stiffness is also going to increase. With that case, I cannot see chaos. Okay. However, if I take negative of the stiffness, it may happen that I can see chaos. Okay. Or also, if I have a very strong forcing and my value of this frequency is also in such a way such that I can experience a chaos, right? So first two cases it is not possible. In the third case, if you see, I have undamped oscillator with no nonlinearity. So this is a very like this in this C option. If you see that this equation is actually not even nonlinear, right? It is written also with no nonlinearity. So this is going to have an oscillation which would have component of both the natural frequency and both the that of the forcing frequency as well. Okay. So I would like to take not take this question. I would like you people to solve this question as a homework because this is not a very tough question, and I've already discussed very thoroughly that how you can use MATLAB to see this, and I want you to do this. However, if you people are not able to go through this question, we can definitely discuss it in the next week's live session. Okay, this is a very easy question. I want you to do it on your own. Okay. Now coming on to question number 9. Okay, so which of the following responds to sensitivity to initial condition? Take the example of Duffing equation. Okay, sensitivity towards initial condition. So when I say sensitivity towards initial condition, what I mean is that as if I change a very small, if I give a very small change in my initial condition, how my response would be after a certain time. Right, so I've already written the MATLAB code for this equation. Okay. So let me just take the parameter value as first as 0.4, sorry, 0.24. I've taken the initial condition as 1 comma 0. And so this is my equation. You know that this is a Duffing equation and it is a ordinary differential equation and of second order, and we are converting it into two first order differential equations and then we are simulating it, right? So I have written the code and now I'll just simulate it. See, okay, again I have to see. Here is my time response and here is my phase plot. If you see the time response, initially we had some transient and then we have a periodic kind of a behavior. In the phase plot also you can see that my system started from this and now it has come to a periodic response. However, since this plot also has the transient elements, so I'll try to plot the phase plot again, removing the transient. So I can plot it like this. See. Now this is my phase plot when I remove the transient. Okay, so you can see that this is a periodic cycle, right? Now, if I change, okay, if this is a periodic cycle, let me just try putting hold on. Now I change the initial condition, let us say 1.1, and again simulate. See what happens. See, what can you see? You can see that it is actually taking the same behavior. Okay, though I have changed the initial condition, but it is going to the same periodic oscillation, right? So my periodic oscillation is not sensitive to initial condition. So I'll just show you that how period doubling happens. So I'll take 2.27 and see. Here you can see that this is not periodic, like not uh, the amplitude is not constant over time. The amplitude is varying. However, if I see the phase plot, now this has the transient, so I cannot say anything. So let us just remove the transient and plot the phase plot again. See, can you see there are two loops, intersecting loops, isn't it? So if there are these two loops, which means that there is period doubling bifurcation has occurred. Initially there was one loop and now there is two loops. So this is period doubling bifurcation. Now if I again change this to, let us say, 2.9 and simulate, now you can see for the period first case there was one amplitude. For the second case there were two amplitudes. Now we have four. And from this I cannot say anything because it has transient. So let us remove some transient and then again plot the phase plot. See, now it has four loops. So again a period doubling has occurred. Okay, and it has four loops. And the time period is going to be 4 times of capital T. And my T is going to come from this omega 1.2. Okay, so now let us take it as 35 maybe. Now this is also not chaos. We cannot say this is a chaotic behavior. It is also a periodic behavior, right? See, this is also a periodic behavior. Okay, what if I take it as 5? Now see, now this is looking something like chaos, isn't it? Isn't it chaotic? You can see that the variation is aperiodic. It is not having any kind of a periodicity, right? So this is chaotic. Now for this chaos, how is my behavior sensitive to the initial condition? See, now I have changed the initial condition to 1.1 and you can see that how my behavior is actually varying. See, initially it was same and after that there was such large deviation. Now when I talk about sensitivity to initial condition, if I take it as 0, 1, so this is the behavior, and then again I take it as 1. See, even if there is a very small variation in the initial condition, see, initial some behavior is the same, however, after that the divergence is very much from that of the behavior. So you can see that my chaotic behavior is going to show sensitivity to initial condition. And that is why when we want to know whether my system is chaotic or non-chaotic, because merely by just seeing the time response, I cannot say that whether it is a chaotic behavior or maybe it is a behavior with a period doubling bifurcation. I don't know, maybe of period 16T. It could be a periodic with period 16T, right? So how do I know whether it is chaotic or non-chaotic? So that the variation in initial condition, the sensitivity to the initial condition is also a way by which we can say that whether my system response is chaotic or non-chaotic. So here you can see that the sensitivity to initial condition is very high. So if I don't know whether this behavior is chaotic or non-chaotic, so I can check it by changing the initial condition, and if it is showing sensitivity to an initial condition, then we say that my behavior is chaotic. However, I will discuss the case of like this also, quasi-periodic, as it will be helpful for you to understand. So I'll take 1.2 into square root of 2 into t. And now I'll just simulate. See, it is a quasi-periodic behavior. You can see a torus. Now if I give some variation in the initial condition, see, there is some variation only initially. After that, it is following the same path. Even the phase plot is same and the time response is same. So if I talk about the question says that which of the following a response shows sensitivity to initial condition. So I saw that periodic is not showing sensitivity to initial condition. My quasi-periodic is also not showing sensitivity to initial condition, but my chaotic is definitely showing sensitivity towards initial condition. That too, very high sensitivity, since a very small variation in the even a very small variation in the initial condition is actually changing the behavior very much. Okay, so the answer to this question would be chaotic. Okay, so okay, I'm done with the questions. So this is it for today's live session. I hope that you people were able to understand what I tried to convey to you. And whatever the questions that I have covered would help you to solve the assignment problems. And if you have any doubt, then you can ask now also, or you can ask in the next week live session as well. Okay,
Thank you, madam.
okay. Thank you. I'll just end the meeting now.